Welcome to the third and last video on the Shale Well Optimizer Python project. In this video, I'll discuss the well design optimization part of the project. As you remember from the previous video, we have the output from the simulator coming in to these two other parts. We have the rates and the pressures coming into the well design optimization part. If you go in and have a look at what's going on within this composite, we see in the first top row, we have the rates coming in from the simulator, and we convert these volumes to revenue streams by using a pricing scheme for oil and gas. Then the revenues are taken into a net present value calculation, where a discount factor is set and the net present value is calculated. The last or lower part of this composite takes care of the cost calculation. First, the well design parameters are transferred from the well model part of the project. And these are transferred into an Excel spreadsheet where the actual cost calculations are being performed. We can have a look at that Excel spreadsheet by double-clicking. At the top, you can see these design parameters that are being transferred every time the project launches. You have the vertical depth of the well, the horizontal length, the number of fractures, and the fracture half length. And then you have some constants relating to the cost, like the cost of drilling one vertical foot of the well and the cost of drilling one horizontal foot of the well. You have some costs related to the fracture treatment and completion of the well. And we have some constants that go into the cost calculation. And then at the bottom, the vertical well cost is calculated, the horizontal well cost is calculated, and the fracture cost is calculated. And these three numbers are then summed together to form the total cost of the well. This number is then transferred into the optimizer and used in the design optimization.
Now?
This cost calculation spreadsheet can, of course, be customized to fit your needs and can be simplified or you can add any complexity you like very easily. If we go back to the Python project, this is again controlled through the optimizer interface. You can go back to the top level and open the optimizer. And here we have the history matching optimization file open. We'll just save this and open the production optimization optimizer file. Here you can see we have again a few auxiliary numbers or constants. We have the discount factor used in the net present value calculation. We have the initial and final price of both gas and oil. And then we have, in this case, one variable set, and that's the fracture half length. And then we have the revenues coming in from the calculation that we just saw in the project. And we have the cost coming in from the Excel spreadsheet. The objective of this optimization is the net present value, which is basically the revenues minus total cost of the well. We could now start and try to optimize this well and optimize the fracture half length and see if any other fracture half length for this well would give higher revenue. And to do this, you simply press the optimize button, and the project will start running repeatedly in the background. Again, you can go to the history window and look at all the results from the different iterations of the optimization coming in. In this case, changing the factor half length, see here, and we'll get a new net present value number for each iteration being launched here. I've prepared a plot of how this optimization actually looks. Here we have a plot of the net present value versus the factor half length. And our starting point was 160 feet for the factor half length here. So the optimization will now try to maximize the net present value and move forward around 280 feet for the factor half length. It'll run for a total number or a maximum number of 20 iterations, and we'll just let it run and see how well it can optimize the net present value.
Let it go.
So now the solver has been running for 20 iterations, and that was the maximum number of iterations we set for this case. So it will now, for the first iteration, it will rerun the best case, which is this case number 19. And you can see that the factor half length has moved from the initial value of 160 feet to about 281 feet. And the net present value has gone from $10 million to $13.5 million.
No.
And every time the project is launched with a new factor half length, the gridding is redone through the gridding utility discussed in the first video to accommodate new factor half length and get the fine gridding around the factor. And the net present value has changed from $10 million to $13.5 million. You could, of course, set up a more complex design optimization by including different variables like the number of factors or horizontal length. But to keep this simple, just use the one variable. Instead of doing a full optimization like this, another option in the optimizer is to set up a case matrix. And you do that by going to the solver drop-down menu and selecting case matrix. Here you can go in and specify values for the variables that you want to look at. You can set up a suite of different values for instance, the factor half length, to study the sensitivity on that variable with respect to the objective. And you can either select a portion of these cases and click run selected to run those cases, or click run all to run all the cases you set up here. And this is a very simple way to look at sensitivities without doing the full optimization. Okay, so to summarize the Shale Well Optimizer practice project, we have a finite difference simulation model for a single well in shale reservoir. And you can either do production history matching with measured data, or you can do well design optimization.